Okay, good day. This is AP Calculus. I am Mr. McCulley, and this is the presentation on Section 3.7, Optimization Problems, or Solving Applied Maximum and Minimum Problems. It's essentially the same thing. So we got a good one today, so strap in here, folks. The good news is there's no new math. The bad news is they're all application problems. So let's talk about the guidelines that we're going to use for solving these maximum, minimum, or optimization problems as they are. First thing you want to do is you're going to read through the entire question, and then you certainly want to identify all of the quantities and the quantities that need to be determined. And what that means is that sometimes they could give you two or three pieces of the equation, and you might have to solve for a third. For example, you could set up a primary equation that needs a derivative, and you need a derivative of a maybe they give you two sides of a right triangle, and you may need the third side. You may have to calculate that before you can move on, and that would be a quantity to be determined. And then, if possible, make a sketch, and we will do that if we can. We're going to write a primary equation, and the primary equation is going to be the quantity that we are going to maximize. That's the thing that we are working towards. Usually, that's what the question is. Maximize this, minimize that, optimize this. That's going to, whatever that is, that's going to be the basis for our primary equation. And then what we're going to do for number 3, we're going to try to reduce that primary equation in such a way that we only have one dependent variables. And sometimes you can't do that. So they'll give you a additional piece of information that you can make a secondary equation and then do a substitution. My first example, we're going to do something like that. Once we've done that, we're going to determine a feasible domain for the primary equation. And, a lot of these application problems, they may have equations that have domains that would be all real numbers. But in the context of the problem, certainly wouldn't, there are certain values that wouldn't make sense. For example, if we are optimizing surface area, we wouldn't be talking about a negative distance or a negative length of a side of a square. Okay, so we definitely have to keep that in mind. And then once we have determined all that, we're going to determine a maximum or minimum through calculus techniques. And this is essentially finding a maximum or minimum on an open or closed interval, which we have already done. So all I got is examples today. There is no new math. Let's get right to it. So first question says, find two positive numbers that satisfy the given requirements. And it says the sum of the first number squared and the second number is 54, and the product is a maximum. So first thing, I need two positive numbers. So we're going to say x and y. These are both positive real numbers, and I'm looking for that. And so we are trying to maximize product. Okay, I can do that. P equals XY. Well, this is a primary equation. And this primary equation has two independent variables, and they are both X and Y. So in general, this product will never have a maximum. Any two values that you can choose, I can add one to either X or Y, and my product will be bigger. But there is a secondary piece of information. The sum of the first number and the second number squared is 54. So x plus y squared, that is a y, is equal to 54. That is my secondary equation. And this secondary equation can be simplified in such a way, say x equals 54 minus y squared, so that I can substitute this expression in for the x, and now say that 54 minus y squared times y equal to 54y minus y to the third. This now is a primary equation with one independent variable. All right, so now I can take the derivative of this thing with respect to y and say, all right, dp over dy is equal to 54 minus 3y squared. No, I did that incorrectly. No, I did it right. They're good. Sorry. And let's see here. We're trying to optimize this problem, and so obviously both x and y have to be positive because they say so. So certainly we can't have a negative there. And we can optimize this by setting this first derivative equal to 0. And so let's factor out a 3. I'll have 3 times, let's see here, 3 goes into 50, 3 goes into 5 one time, 24, 8 minus y squared equaling to 0. And so my values for y that make that thing equal to 0 will be the square root of 18, which would be plus or minus 3 square root of 2, I think. Yeah, that's what it's going to be. And so obviously the negative one won't work. The positive one will. And so we only really have one value that makes sense in the context of this problem, and that's y equals 3 square root of 2. Now we could go through like a number line, say as a for instance. We can't have any y value that's less than 0, but we certainly have a 3 square root of 2 value. And so from 0 to 3 square root of 2, obviously 3 is going to be smaller than 3 square root of 2. So I could plug that in, and I could say 54 minus 3 squared is 9 times 3 would be 27. And then 54 minus 27 would be a positive value, right? And then if I pick, say, we'll pick like 5 over here. If I plug in 5, 5 squared is 25 times 3 is 75. That's going to be a negative in this interval. So it's increasing to 3 square root of 2 and goes down after that, becomes negative. So obviously this is going to be the maximum value for the product. Now this is the y value. And so let's see here, to get my x value, get x equal to 54 minus 3 square root of 2 squared. Well, 3 squared is 9, square root of 2 squared is 2, 9 times 2 is 18, and then so x equaling to 54 minus 18 is 36. So my two numbers are 36 and 3 square root of 2. Those are my two values. All right, let's look at another one here. Okay, number 24 from that page. It says, determine the dimensions of a rectangular solid with a square base with maximum volume if its surface area is 337.5 square centimeters. Oh, surface area problem. Okay. So let's talk about this thing. I'm trying to, let's see, maximum volume. So my primary, maximize volume. Volume equals length times width times height. Well, here it's even worse than the last one because I have a function that has 3 independent variables. So I gotta simplify some stuff here. Well, good news, got a square base. That changes one of these into just 2. So if, again, let's, you know what, let's just real quick draw in a little rectangular solid. I know that looks like a square solid, doesn't it? Oh well, we'll live. So if I say this is length, this is width, this is height, well, because it has a square base, I can go v equals L squared. Yeah, let's go L squared plus 8 or times h. Well, that's good. Now we've reduced that thing down, or that primary equation, to an equation in 2 variables. There's not a whole lot I can do because the height isn't required to be the same. And I do have a surface area maximum requirement. Now let's talk about surface area. Surface area is going to be the sum of all of the areas of the sides. Now, since it's got a square base, it has to have a square top. So that's going to be 2L squared. And then each of these sides are going to be rectangles. They'll have a height of h and a length of L. So let's go LH. And then let's see here, there's going to be a front, a back, a left side, and a right side. And I think I did that backwards, but we can count them to be 4. That's a 4, not a Y. And let's see here, we know that the surface area is 337.5. So 2L squared plus 4LH. Now, what I want to do is I think I want to try and solve this thing for H, and then if I have only values of L, I can replace that. Now, could we solve for L and then have a function of H? I think we can, but I didn't do it that way, so we're going to solve for H. Anyway, so I bring this to the other side, I divide by 4L, and I get H equal to, let's see here, it ends up being 337.5 minus 2L squared all over 4L. And that thing we can reduce to, let's see here, let's make it 337.5 over 4 to the L minus 1, and then it'll be minus a half L. Now, I'm going to plug that in here. So I've got V equal to L squared, and then multiply by, because I'm replacing this H with this expression here. So I've got 337.5 over 4 times L to the negative 1 minus a half L squared. Okay, that looks good. And so I want to multiply this thing. I want to multiply it out here. And so L squared times L to the negative 1 will give me that 337.5 over 4 L now to the first power minus 1/2 L to the fourth power. No, made a mistake here, folks. Look, I have a half L to the first here. I don't know why I changed it to a half L squared right here. So let's change that back. And then this will become L to the third. Yeah, that looks better. Yeah, I like that. All right. And so now we can do the derivative of this. We know V prime. And you notice I'm using different notation, and I'm doing that on purpose so that you see the different notation and realize that in this case I used the differential notation, which we'll be talking about later, and here I used the V prime notation. Anyway, this thing just becomes 337.5 over 4, and then this one becomes, it's not equal to, it's 3/2 L squared. Now, again, to get an optimum value, we're going to talk about anywhere where we have a critical number, which would be where the derivative is 0 or undefined. And if I solve this for 0, it's you subtract 3. Let's just write some of this down. I already skipped a couple steps. It's squared. It'll be negative 337.5 over 4. I've got a negative and negative, so I can make it a positive. I divide both sides, so by 3 over 2, which would be like multiplying by 2 over 3. So L squared equals 337.5 over 4 times 2 over 3. And then I take the square root of that, so L equals plus or minus the square root of this expression, 337.5 all over 6, because the 2 cancels with the 4, and I got a 2, and 2 times 3 is 6. And the crazy thing, this comes out to plus or minus 7.5, which I thought was just nuts. All right. So obviously we can't have a negative length, so no negative. So our 7.5 is positive, or is the only possible critical number. And since there's no top value that I could use for any of those, either the height or the length, certainly we could use that number line again, but this is the only one that it could possibly be. It's not going to be 0. And since there's no top to close the interval, this is the only value that'll work. Now, if I go back to this equation and I find h of 7.5 here, going 337.5 over 4 times 7.5 to the negative 1 minus a half times 7.5, I get, and this is also crazy, if you type this in your calculator, and you can do that, and you should do it, just to check me, I get 7.5 again. And it's crazy that I have that. And remember, our units for all of these, since it's a solid in centimeters, it says that if my length and is 7.5 centimeters, and my width is now 7.5 centimeters because the length and the width are the same, and my height is 7.5 centimeters, then the optimal surface area, or give me the maximum volume using that surface area, is if I make it a cube. And that makes a lot of sense, because it makes sense to say that if I have a given surface area, I should make all of the parts equal, and that will maximize my volume. So there's my answer there.